Okay, welcome back, GIS guys and girls. Today, we are going to calculate the volume of the Berkeley Pit. So, you're going to get to go through the same steps that I went through. When I tried to develop this lesson plan, I discovered that the Anaconda Mining Company, who originally developed the Berkeley Pit and was taken over by BP Arco and to some extent, Montana Resources still works on the Berkeley Pit. They had a proprietary survey system for the Berkeley Pit that didn't match up with any world coordinates I could give you. So if you would please open a new blank instance of ArcMap and bring in from the geodatabase I sent you 2 different files. I would like for you to bring in the Berkeley Pit raster. It's a graphic showing the Berkeley Pit from Google Earth several years ago. The Berkeley Pit has been well, it's changed quite a bit, and this graphic seems to be one of the best ones from that matches really well to the contours I was able to get for you. So if you'll bring in that image of the Berkeley Pit, this has been previously georeferenced for you. A lot of this perimeter has disappeared as the pit fills in and whatnot. So this is an old graphic. If you could also please bring in this ARC 4250. This is a contour of the Berkeley Pit, and it was actually done in the coordinate system that was originally developed by the Anaconda Mining Company. This is the Anaconda Mining Company's original graphic of where their coordinate system existed, and I'm sure you could look up where the 0 point was and go through georeferencing this perfectly to their original coordinate system. But because it's proprietary, you have to have some sort of insider to get that information. I wasn't able to find it, but I know that this is the contour of the Berkeley Pit when it was empty. And I have a pretty good idea of how to georeference that. Just based on looking at this shape, you can see we have a really similar shape. So here's where your georeferencing skills are going to come in handy. You're actually going to put them to real world use. The first thing we want to do is take a look at this file. This file originally came in with this coordinate system assigned to it, but I removed that coordinate system because it didn't work. We would like to turn this into something that we can georeference. Now you can't georeference a shape file. You can see this is a line shape file. So what we want to do, we want to turn this into a raster because you can georeference a raster. Open up ArcToolbox for me if you're following along. There's my ArcToolbox, come on. My Zoom panel is getting in the way and it's preventing me from opening ArcToolbox. Put ArcToolbox over here, docket. I'm looking for a conversion tool because I'm going to convert from a line shapefile to a raster. So I'm converting to a raster. Polyline to raster is the tool I'm looking for. And if you can't see this on the screen, I opened up ArcToolbox, went into conversion tools, expanded to raster, and went down to polyline to raster. So my input feature is that shapefile ARC4250. All that means is that this is the 4250 contour line, and I believe it's a 50-foot contour interval, each of those contours. The value field should be Z, because if we open up this shapefile and look at the Z value field, this is that contour interval. We're looking at a 50-foot contour interval. We want that Z value field to be the piece of information that the raster is built from, because we're eventually going to go back and do something with this to calculate that volume. So let's set the cell assignment type to maximum combined length, and our priority field can stay none, but we want our cell size to be 10 meters. So change that 28 to 10 and say OK. Actually, before you do that, before you hit OK, let's make sure it's going to the right place. I wasn't paying attention. I'm just putting it in my output data set. I want to put that in my geodatabase that I'm working from. So I'm going to put that in the Berkeley Pit geodatabase and name it line to raster. OK. Okay, I paused the recording because that usually takes a few minutes. So if that took a while, it's okay. That's pretty normal. So this new raster, if we zoom to layer, looks the same as the shapefile, but notice it's now a raster. It's actually a continuous symbology here, and we can change that to whatever you want. Make that a color ramp or something so that you can see that that is actually continuous and shows just where those contour lines are. And they are based on the depth here, the depth of the contours. So now we have this contour raster file, we can georeference it. Now there are some features here that I want you to identify when you try and georeference this. See this sort of almost triangular edge here? If we zoom into the Berkeley Pit, you'll see that image. You can look for these kind of pointed features throughout the image itself to georeference to. So we've got this kind of the base of this triangle over here. We've got the edge of the pit over here that's kind of angled. It looks like there's a road running through here that's going to create that sort of flat area, and then there's contours over here. So we're going to set this up to georeference. I need to turn on my georeferencing toolbar, so I'm going to go into Customize, Toolbars, Georeferencing. So now I have my georeferencing toolbar. I want to make sure my line to raster is showing up in the georeferencing, and that's the tool it's going to georeference to. I'm going to open my viewer window because I prefer to do the viewer window as opposed to looking at the two at the same time. This is entirely personal preference. And I'm going to uncheck my line to raster because as I put points in here, it's going to show up on my map and it's going to obscure my map. And I want to look at both of these at the same time. So back up here on my georeferencing toolbar, I'm going to add my first control point. This little lip on the edge over here looks like a good one. It's kind of visible here. Now I want you to understand that this is very general. Your numbers at the end of this are going to be different from mine if you're following along. It's totally okay. This georeference is pretty broad brush. So get it as close as you can, but don't kick yourself over not getting it perfect. So I'm going to use that point and apply it there. It disappeared from my viewer window, so I'm going to use my little world viewer to bring it back in. And remember, when you're doing these control points, always go from the raster that you're referencing to the raster that you're referencing to. So if I move this over a little bit, another point that looks pretty easy to spot is down here at the bottom of this kind of triangular area. Looks like there's a kind of an almost jagged edge here. So I'm going to use that as a control point and apply that point. And this has jumped on me again, so I'm going to go back and blow that back up. Now I've got these 2 points. I'm going to look for a point up here in the top of the map now, somewhere that's kind of visible just to spread my points out as much as possible. It looks like this flat area right here is this road. So I'm going to say that this kind of point area, I'm just going to assume that it's right about here. Let's see how that looks. So now I'm going to close my viewer window and just see how this overlaid. If I turn this back on, that's not too bad. I'm probably a little bit off. It looks like the road is right here, but it's following pretty close. And for our purposes, that is definitely good enough. Now I just happened to get away with 3 points. That's not typical, but like I said, for this, we're just trying to get a general idea, and we're going to use this to calculate the volume. That's probably good enough. So I'm going to go ahead and rectify this. So remember, if you want to update this, rectify will create a new file, but update will assign the georeferencing coordinates to the file you already have without any redundancy. Personally, my preference is usually to rectify in case there's any problem. I can go back to my original file. So I'm going to rectify and make sure the output location is where I want it. I'm going to put it in that Berkeley Pit geodatabase. Name it. bottom raster because this is going to be the bottom of the Berkeley Pit. These are contours going down into the Berkeley Pit. And just say save. So now, going into my catalog in the Berkeley Pit raster, I'm going to bring that bottom raster in and get rid of my line to point raster. And I'm going to, just for the sake of visibility, put this in a color scheme that hopefully you can see a little better. Let's do red to green. Hopefully that'll show up a little better on here. Looks like that's a little more visible. I hope you guys can see this in the standard definition on YouTube. So I do want to point out the difference between update and rectify are sometimes whether or not you can actually use the tool. We're working in a geodatabase, and I believe that they've corrected this in the geodatabase, but certain raster files cannot be updated. They can only be rectified. In this case, we created a grid file because when we used this tool, Polyline to raster, we didn't specify a file type. If you go in here and it says no file type is, or no file extension is specified, an ESRI Grid raster format is defined. Since I didn't put a file format on that, it came out as a grid. Now, I didn't mention this when I was doing it because it's just sort of, ESRI Grid is a great file system to work with, and I tend to default myself towards ESRI Grids. But if you want to use a JPEG or a TIFF or any other file format, that's fine, you can still do that. But just know ESRI Grid works much better in this software. It's their own format, and grids do not update. You cannot update a georeferenced grid. You have to rectify that. So in this case, stick with rectify if you were doing this outside of a geodatabase, because you're not going to be able to update that file. So let's zoom back into the Berkeley Pit. Looks like my software is thinking. So I'm going to zoom to layer to look back at the Berkeley Pit. Next thing I want to do, I don't have a contour of what the top of the Berkeley Pit used to look like. I don't know what it used to look like. So what we're going to do, we're going to calculate a surface based on the perimeter of the Berkeley Pit as it currently exists. So you know how to create a new shapefile. We're going to create a new polygon shapefile, and we're going to draw the perimeter of the Berkeley Pit, and we're going to take only the contours that are outside of that perimeter. So go over here into our catalog, pick where you want to work. I'm going to continue to work in my Berkeley Pit geodatabase. Right click, new feature class. I want to create a polygon feature, and I'm going to name it perimeter. Let's put it in a coordinate system. I'm going to use UTM zone 12 north. So that's UTM, or Universal Transverse Mercator, North America. Oh, nope, sorry, I'm leading you astray. My bad. Come back up. Actually, let's do state plane because I've forgotten where UTM is. So we'll do state plane, NAD 1983 meters, and pick out Montana instead of having you hunt through UTMs to find it for me. Select that coordinate system. Looks like my computer's freezing. Okay, there we go. So choose that coordinate system. We can leave the XY tolerance to the 0.001 default because we know that we're a little bit off. This is an extreme tolerance. We know that when we georeference that, we're probably not anywhere near 1,000th of a meter inaccuracy, but we'll leave it alone because we don't know what the accuracy actually is. Just say next, keep going through these until finish. So now we've got this new blank perimeter shapefile. There's nothing in it, but we want to draw that perimeter. So to do that, we need to get our editing toolbar open. So let's see. I need to go into Customize, Toolbars, and turn on my editor toolbar. Now I've got my editor toolbar. I want to go into editor, do that little drop screen, go down to edit windows. If you don't have your create features window, oh, I've got to turn editing on. So let's first start editing. Continue. I want to edit my perimeter shapefile, so make sure you've highlighted perimeter. If your create features window doesn't show up over here, go to editor, drop that little menu again, go down to the bottom, editing windows, create features. We want create features to be open and make sure you've selected perimeter. So we want to draw a polygon for that perimeter. Now just sort of pick your way around the perimeter of the Berkeley Pit. You don't have to be exact. We want to try and stay. Oh, my computer's being really slow. Sorry, guys. It's taking its time catching up. Okay, there we go. Just pick your way around. Remember, one single click will put down a vertex. A double click will finish your polygon. So let's just go all the way around and sort of pick out the area that defines the perimeter of the Berkeley Pit. So that's my approximate Berkeley Pit perimeter. I'm going to make that hollow so you can see it and blow it up. There we go. That's what I'm calling the approximate perimeter of the Berkeley Pit. You can use that graphic and decide what you think it is. Just remember, when we do these calculations, yours are going to be a little bit different from mine. So the next thing we want to do, we know where the perimeter is. We have contour lines inside and outside of that, but we don't have information on what the original pit surface used to be. So what we're going to do is take this contour information and assume that if the surface is as flat as possible across here, so that we can calculate what that volume is that's been removed underneath that flat surface. To do that, we need to go from this bottom raster back into a point file. We need to convert this to a point file with a Z location. So to do that, first, let's finish that drawing. Let's tell editor to stop editing and save the edits. Looks like I'm on hold again. My computer is being particularly slow. Editor, stop editing. Yes, I want to save my edits. So now I've completed that perimeter shapefile. I can move on to something else. Oops. I want to go into ArcToolbox. And this time, I'm going into conversion tools. I'm going from a raster. So expand the from raster to point. I want to go raster to point. This time we're taking that contour raster and turning it into a point. So raster to point, we're choosing bottom as our file. The field value is value. That was the X, or I'm sorry, the Z interval we assigned as the value for the raster. That's the contour interval Z. And we want to make sure we name this. Put it in your Berkeley Pit geodatabase or whatever you're using, but name it points, or elevation points would be more specific. And say OK. All right, so that might take a minute, but you're going to see you've got quite a few points in here. What that did was it took those contour lines that we had turned into a raster in order to georeference, and now it's turned those contour lines back into points. So all along one of these contour lines, that point has the same elevation information. If I can open the attribute table. So if I open the attribute table, you'll see all of these fall on that grid code falls on that 50 point line. If you sort this, you'll see that you've got contour lines. You'll have a whole bunch of points that fall in the same contour line. So we've created this perimeter, and we've created these points. What we want to do now is select by location. So go up to select by location, and we're looking for all of the points that fall outside of the perimeter. So we're choosing from the elevation points anything that is outside of the perimeter. So I don't have a particularly good way to do that from this drop menu, but I can say anything that's inside that contains the source layer feature. Let's see how that selects. Oh, I did it backwards. That are within the source layer feature, my bad. So I can grab anything that's inside and then close that out. We know how to switch our selection in our attribute table. Open our attribute table and switch the selection. Sorry, if this seems halting, it's because my computer is being incredibly slow and it freezes up on me periodically. So I paused the recording to keep you guys from having to sit here and wait for my computer. So this little icon up here, switch selection, we just click on that and now we've grabbed everything outside of the perimeter. So using the tools that you know how to use, select by location, a few conversion tools we just added, but you know how to draw a shape line file. Now we've done this. So now we can export these as just a single separate file. So right click, once they're selected, data, export data, and put them wherever you want to put them. I'm putting mine in that Berkeley Pit geodatabase. So I'm going to call this outside and say, okay. Yes, I want to add it to the map as a layer. So now that I've created this new layer, I'm going to clear the selected features. You can't really see that they're different. So I'm going to change the color, make them yellow. So now you can see I have the elevation points in green and the outside elevation points in yellow. I'm going to run the same tool twice because what I want to do with this now is interpolate a surface. I'm going to create a raster surface that will allow me to interpolate or basically draw a flat surface across the top of the Berkeley Pit and then interpolate the inside as well that includes the bottom of the Berkeley Pit. So to interpolate, we need spatial analyst. I'm going to open up my spatial analyst toolbox, go into ArcToolbox, collapse everything in spatial analyst tools. We want to scroll down. Spatial analyst is near the bottom of ArcToolbox. Want to scroll down and expand interpolation. In interpolation, we have 4 different tools that will interpolate the surface: inverse distance weighted, or IDW, creaking, natural neighbor, and spline. These all do the same thing, but they do them with different algorithms. Let's use creaking for this one. So open the creaking tool. I got this message, tool not licensed. If you did not get this message, good for you. You've already got your extension turned on. But if you did get this message, say okay. Unless you're using something outside of campus or outside of the version that I gave you, this will work. We have the spatial analyst extension, we just have to turn it on. So go up to customize, expand that, and go down to extensions. Under customize extensions, check the spatial analyst extension. Just make sure that's checked and then you can close that. Now go back into ArcToolbox, click on that creaking tool again, and this time it will open. So let's do the bottom first. We want to creak the bottom, and that means our endpoint ID features needs to be elevation points. That's the one that includes all of the points. Your Z value field should be grid code. Unless you changed the name somehow, grid code is what's been assigned as the Z elevation field. So make sure you know where it's going. We want to put this into my Berkeley Pit geodatabase and say pit bottom, or I'll just say pit bot. I know what that is, save it. I want my output cell size to be 10. Previously, we set our cell size to be 10. When you're working with rasters, when you're doing raster calculations, your rasters have to be the same cell size. So let's stick with 10 because we're going to use 2 different rasters to calculate the volume in between them. So I'm setting my output cell size to 10. Everything else you can leave alone and just say okay. That's going to creak away for a moment. And as soon as that comes up, we're going to get a colorful image that is essentially the smooth surface based on those points and the elevation of those points. We're going to do that twice. We're going to do it again the second time for only the points that were outside of the perimeter. So the idea is we're creating a continuous smooth surface through the bottom of the Berkeley Pit, and then we're creating another one that goes across the top of the Berkeley Pit and excludes everything in the middle inside that pit perimeter. And it's still crunching away. Here it comes. All right, there we go. So I'm going to turn these points off. You can see this is a continuous surface. You can split this up. This is no longer a contour. Every single cell has a number now, but they've created a continuous surface all the way down to the bottom of the Berkeley Pit. Now let's run that creaking tool one more time. This time we want to use the points you saved as the outside of the Berkeley Pit. Remember to set the Z value field to grid code again. Set your output cell size to 10 again. And wherever you're putting it, let's call this pit top. And let that creak away. Now this time it will not look like a bullseye sinking into the bottom. It's going to be a more continuous surface because we don't have the information for what it originally looked like. But we now have a kind of smooth surface that basically slants across the top of the pit. So what we're looking for is the difference between the top of the pit and the bottom of the pit. I'm going to turn off the arcs and the points now. We're only interested at this point in, oh, well, I guess I'll leave the Berkeley Pit turned on. We're only interested in these two rasters at this point. We've created a smoothed raster of the top and a smoothed raster of the bottom. There's one more tool that will calculate the volume for us, and that is called the Cut Fill tool. Go back into ArcToolbox, back into Spatial Analyst, and collapse interpolation, and scroll down to Surface. Under Surface, we have this tool Cut Fill. Open that tool, Cut Fill. We want input before raster surface will be your top. So pit top. Input raster after surface will be your pit bottom. So we're subtracting one from the other. I want to name this and make sure it's going into my Berkeley Pit geodatabase. And I'm going to call this volume. Say save that as the volume. But pay attention here to your Z factor. The numbers over here, the contours, are in feet. But at least I assigned the coordinate system to be state plane meters. So the difference between the XY coordinate system and the calculation for the contour itself is a factor of let me look at it, 0.3048. So 0.3048. That is calculating the difference between the feet and the meters in the X, Y, and Z direction. So if you open your help menu, it'll tell you that over here. Here it is, 0.3048 to convert your Z units from feet to meters. Because our XY is in meters and our Z is in feet, we need to assign this number. And you can say, okay. All right, that came up pretty quick. That one wasn't too slow. So it's not perfect. Everything on the outside here is due to just creaking a little bit different, but this is the volume we're interested in. See over here, the volume says net gain and net loss. If you want to make this perfect, you can actually clip this raster to the perimeter before you run this calculation. That would be the best way to make this absolutely perfect. But in the meantime, let's take a look at the attribute table of this raster. So the volume here, we can run statistics on. I'm going to calculate the entire, we're just going to do basically a summation of this volume. So if you right click at the top of that volume column and say statistics, it's going to give you the total sum. Now remember that this is in cubic meters. We've got, gosh, looks like 386,912,000,000, or no, sorry, I'm reading this wrong. My bad, it's too small of a screen. It's 386,912,417 cubic meters. Okay, so your volume again will be a little bit different. And if you would like to take this even further and get the exact calculation inside this perimeter, you can always do the ArcToolbox clip. Remember, it's not the analysis tool, it is the data management tool, raster processing, clip. This is how you clip that raster to the shapefile. So if you want to do this volume calculation, you can clip both of your rasters, the top and the bottom, to that perimeter shapefile and rerun this calculation. And that'll get rid of everything here outside of the pit. But you have to do that after you've created the two surfaces. So let's see what that was. Cubic meters doesn't mean a whole lot to me. So I am going to run the statistics on that, copy that sum, and see what that volume is in yards. Man, that's a lot of material removed. And now keep in mind, realistically, if we had the original surface of this would have been more of a mountain. We're just talking about what's missing right now from below the surface. But that's a whole lot of material that was removed from the Berkeley Pit. So not the most exact for true real life calculations, but this is how you go about calculating the surface when you don't have the information that you're looking for. I think that was all I wanted to show you with this one. Yep, that was all I wanted to show you with this one, but I do want to point out one more tool. I'm going to turn off the volume. That was the entire point of running the volume of the Berkeley Pit, but there's one more tool I'm going to show you while we have this, and that's how to create the original contours. We have this raster file. I turned on my pit bottom raster file. Now I want to contour this at 50-foot intervals. I'm going to go in, back down in my spatial analyst. In surface, I have a contour tool. So let's open contour up. I'm going to input the raster pit bottom. We're going to basically recreate the contours we originally started with, but this time they're georeferenced. I'm going to put them in my Berkeley Pit geodatabase. I'm going to say contours. Save that. I want my contour interval to be 50 because I started with a 50-foot contour interval. That's where I'm going to start. My base contour, let's see, it looks like we can start a base contour. Let's do it at 4250 because that's what the arc said it started at, 4250. So let's make a base contour of 4250. Z factor can stay 1. Actually, I think we need to change that because this wasn't the one that we did the, this isn't the volume calculation. So we do need to change this one again to 0.3048, I believe it was. Yep, 0.3048. And we want to contour it, and that should be all you need to say. We can leave everything else alone, say okay. This is going to create those original contours that came from the ARC 4250. So here we go. Let's take a look at that. I'm going to turn the pit bottom off, and I'm going to turn off the Berkeley Pit background so we can compare these two. Here's the original bottom file. So it looks like, ooh, I did something terribly wrong here. I missed a giant contour interval, but you can see we basically contoured back out a 50-foot interval what that originally looked like. I'm going to make that a color you guys can see a little better. So here are my dark blue lines. Here my dark blue lines are what I created to contour, and you can see they map really closely to the original contour lines because all of the data came from the original contour lines. But this gives you some confidence that what we're doing is actually based on data. So that's how you run a contour. That has nothing to do with calculating the volume. I just thought you might want to take a look at using that tool. So let's see. That is all I have for calculating the volume of the Berkeley Pit. Hopefully you guys are able to follow along with that. If you have any questions, give me a call, shoot me an email, whatever. But all of the information to do this tutorial is going to be included in the email I sent. All right, stay safe.